So, I'm going to tell you a little bit about the work that's going on in my group, and I'm going to serve as an introduction and a hype man for Sean. So just hit the play button up there. There you go. So this is primarily work that's been done not by me, but by graduate students working with me primarily. Today I'm going to talk about work by Sean. Also, there's a talk on Thursday from Tim Carlton. He's going to talk about some related things. And then I'm going to hopefully have time to present work from Katie Rodriguez-Wimberly, as well as a former student, John Phillips, who's a postdoc at Minnesota. So I'm going to talk about quenching at late times, and in particular, I think this plot illustrates why it's interesting to think specifically about satellite quenching. So this is a plot that shows lone observations relative to semi-analytic model from Guo et al. It doesn't matter which model you pick. We could take Galform, you could pick a hydrodynamic simulation. You're still going to get this wrong. I challenge you, go for it. But basically, if you plot the quench fraction for satellite galaxies as a function of stellar mass, what you find from Sloan is that if you do this for centrals, all galaxies and satellites, but just specifically focus on the centrals, the orange and the green, the satellites, you see that you do okay for centrals. Great job. Whatever the physics is there, whether it's AGN feedback, I'm not particularly concerned at this moment about that, but you do all right. But things are really bad for satellite quenching, and so I think this is the most interesting topic to be focused on. And in particular, you see that in general, the models are too efficient in their quenching. So at this point, I'm going to disregard all work from the model front because clearly it's worthless, right, Richard? We can agree, thank you. So we'll just let the observations lead the way. Definitely the best approach. And if we do that, what we see is we can... Oh, damn it. All right, so if you do that, if you let the observations lead the way, you can go into Sloan, you go into various data sets, and you can actually quantify what is the efficiency of satellite quenching. And so you do this by looking very simply at the field population, and then you look at the satellite population, and you compare the quench fractions. And you can therefore infer, at least as of today, what is the efficiency of satellite quenching, where 100% would be everything that falls in is quenched by today, 0% would be nothing gets quenched. And so if you do that, you can plot that as a function of stellar mass, and we find a couple things. First of all is that quenching, unlike in the models, is relatively uniformly inefficient at late times. This is also interesting relative to what Casey showed yesterday, or maybe this is not the case at higher redshift. Maybe there's more of a mass trend. And then interestingly, as you go to lower masses, which we can really only probe in the local group, you see that there's this increase in quenching efficiency towards very, very efficient quenching. And so I think this is an interesting plot, but I think at the end of the day, this isn't that physically motivated, and so we'd like to move to a more physically motivated picture. And the way I want to go about doing that is by connecting these observations to Nbody simulations. In particular, we used a variety of different ones. We used Millennium, Bolshoi, Joel, don't worry. But in particular, we used Elvis for a lot of this work. So for those who don't know Elvis, I guess you all do. I'll just skip this because probably Shay talked about it over the course of a couple of years. And so these are simulations of local group-like pairs that have very good mass resolution for our purposes. And so the way I view Elvis is a little bit more like this. So these are I'm going to take you through what we do. This is our Nbody simulation. This is a host halo in green. That's subhalos, either here and then less massive field halos. And so what we do is we go into Elvis and then we populate the subhalos or any halo according to abundance matching. We just assume a stellar mass halo mass relation. So they're my galaxies. And then what we do is we begin to play games about, in terms of tuning a quenching timescale, to see whether we can reproduce the quench fraction. And so I've set up a couple simulations here. I'm very proud of these. So trust me, if you knew how long it took to make these in Keynote, you would be moderately impressed. So here's my satellite. It's star forming now, hence the blue background. It's going to fall in, and I set a quenching timescale set by when it crosses the virial radius. And after that amount of time, I'm going to quench it, right? And so I can do that. Oh, I got multiple, that's right. And boom. And then so, right, we get a given quench fraction, and I can do this with a longer quenching timescale, and not surprisingly, you get a lower quench fraction. So it's not all that complicated. Just paste on galaxies, run them forward, assume a quenching timescale, you get a quench fraction. You can just tune this quench fraction to match the observations, right? So if you go ahead and do that, the upshot is something like this. So this is the quenching timescale for satellite galaxies. That is time in gigayears after they cross the virial radius to when they quench, as a function of the mass of the satellite galaxy. And here, we're blurring together a somewhat broad range in host halo mass, okay? And so these are results from Andrew Wetzel, and then some work from Coral Wheeler, and then Sean Fillingham pushed this to lower masses. And so I think this is a very interesting result. You see some very striking trends, obviously. This increasing timescale as a function of mass here, and these very short timescales at low masses. And so I'll spare you some of the details. The upshot is I think we have from this an interesting physical picture, which is if you look at the high mass end in particular, it's very difficult to come up with a physical scenario where we get very long quenching timescales, right? All of the environmental mechanisms people propose would tend to hurry quenching, whether it's stripping, whether it be ramp pressure or tidal, mergers, whatever you want, that all speeds up quenching. But we need long timescales. So the thing that gives you the longest timescale is actually starvation. And conveniently enough, these timescales match the typical gas depletion timescales you would see for field galaxies. So suggesting a picture that looks something like this, where at high masses, satellites fall in and are starved. They're cut off from further accretion. They burn through their remaining gas, and they quench. And so the quenching timescale goes like the cold gas depletion timescale, where you actually need to include molecular and atomic here, the full gas reservoir. And this roughly agrees. If you want to see the details, see Sean's paper. And then at this sort of critical scale for quenching that's probably dependent upon the host halo mass, you see that effectively you're able then at lower masses via the mass of your CGM, the density of your CGM, the infalling velocity of your satellites, your ramp pressure is actually able to kick in and able to strip satellites and get a quenching time scale that goes like the dynamical time. So, as I say, I'm trying to channel Avishai a little bit. That it's my toy model of satellite quenchification. But I think there's some open questions. So, here are some of them. I hope to get through a few of them, including, is the local group cosmologically representative? The whole low mass end of that plot is all motivated by the local group. And then there's some further details. And so that we have a bunch of papers coming out. There's no way I'm going to talk about all this. Sean will get to some of this late in the next talk. But so I want to talk, is the local group representative? And specifically, are the global properties of the satellite population representative cosmologically? That is, when you look in the local group, at low masses, below 10 to the 8 in stellar mass, all the satellites are dwarf spheroidals for the most part. But what about when you look at other systems? So there's a recent paper from Marla Jiha and company, the Saga survey, that did this amazing bit of work, just impressive. They targeted Milky Way mass systems in the local universe, and they went out and they collected thousands upon thousands of redshifts in the area surrounding those Milky Way mass systems, and they found the 2 satellites that they could out of those 2,000 to 4,000 spectra, and they were able to then identify a satellite population. And the upshot is, you can see here, so these are their satellites, and here they are plotted, size a function of absolute R-band magnitude. Effectively, they're all, color coding means are they star forming or not. You can see they're all star forming down to, they say they're complete down to a Leo 1 like mass, so below 10 to the 7. The upshot is, this is not what the local group looks like at all. So controversy is always a little bit good. I think that's probably some errors there. So what we've been doing is a different approach. So we're doing this photometrically. I don't have time for taking that many spectra. So what we're doing is we're taking a Milky Way host. So you pick something out, Milky Way mass in the local universe, take the photometry in some deep survey. In this case, it's CFHTLS, but you could do this in DES, hyperstream data. And you put down annuli, and you count up the number of faint objects surrounding the Milky Way, and then you do the same in a random field, right? We have not selected on. It could be. I don't think so, but I don't think so. So if you do this, and if you just count up the number of objects, so this is average number of galaxies across sample of 1,000 Milky Ways minus 10,000 random fields. This is actually a plot I made in one afternoon as a proof to my student that you could do this. He has a much better version now, but the upshot is this excess right here, that's the satellites, right? Those are the satellites around the host. I can't tell you which ones are the satellites at all, but I don't care which ones, really. So that's great. I can identify the satellites, but then the question is which ones are passive, which ones are star forming, and for that we do a little bit of machine learning. So we take the photometry where we just have GRI. We can't detect them in U and G, they're too shallow, or U and Z, they're too shallow. And then you use a training set from Sloan and gamma spectroscopy, and you can infer, just using the GRI, which ones are star forming and which ones are passive. I see some faces that this is a bad idea. I say, you might be right. So this is our result. This is the satellite quench fraction as a function of stellar mass of the satellite. And so you can see these are some of those points from before, and then these are the local group in green, and what we get are these points here. And so I think, you know, interestingly enough, we're a little bit high here. So I think, you know, this is sort of a point you might anchor and say, do we recover this set of data that's purely spectroscopic? We do an okay job of that. But the interesting thing is that we definitely see this uptick towards low masses. And so the upshot, I'd say this is preliminary, but the upshot is that the local group is relatively typical. So you can trust everything I just said for the first 10 minutes of the talk, because it's meaningful, because the local group is meaningful on cosmological scales. All right. So this gets us back to this picture, which is clearly then you should now be starting to take as gospel, if you haven't already. But so what about comparing to star formation histories and field constraints? So I'll skip over the star formation histories, right? We have detailed star formation histories for a whole collection of local group satellites from Dan Weiss, others. And he's already done a lot of work looking at this, and they agree very well with what we find for our quenching timescales. But the field constraints, I think, is interesting, and in particular, this not too well appreciated fact, which is that when you look just outside the virial radius of a dark matter halo in a simulation, a large fraction, so this is from Shea's Elvis paper, this is the fraction of halos outside of RVIR, right? So this is starting at 1 RVIR, 2 RVIR, 3. Roughly 50% of halos just outside RVIR were once inside RVIR. They were once satellites, they were once subhalos. And so if we have a very efficient quenching at low masses, you might be worried that we're going to overproduce the field quench population because there are not that many passive systems surrounding the local group. There's a few that we know of, but not that many. Most things in the field are star forming. And so the upshot is, don't worry. Our model works just fine. So here you have, this is from Sean's upcoming paper. So this is the quench fraction as a function of R veer. So these 2 points are satellites, these 3 points are satellites, and then here's our one field point. It's not that good of statistics in the local volume, but basically you can see the short quenching timescale that we needed to reproduce the satellites also reproduces the field. So if you look at the purple line, it roughly matches the field quench fraction. So not only does our model of satellite quenching give you what's going on with satellites, but it can also give you the field quench fraction. We don't have to worry why field galaxies are quenched. All right, so now I want to conclude by talking about what's going on at the lowest masses. Our plot impressively spans 5 orders of magnitude in satellite stellar mass, but there's more room, as BK showed yesterday. There's a lot more dynamic range in this plot. We're going to stay shy of globular clusters, but we'll get close. So you might say, what's going on at the lowest masses? Right? There's been basically everyone's assumption going into this is reionization, right? Spoiler alert, I think you're correct. But do we actually know that? When you look at the star formation histories of the lowest mass satellites, as Mike showed, you find that they're all preferentially old, but there is some scatter, and as Dan Weiss has argued, there's some reason to think that environment could still explain the star formation histories and the quenching of ultrafaints. Well, so what we've done is we've looked at this in more detail, and in particular, we're concerned about this environment angle, in particular because the ultrafaints that have been studied in detail, I'm focusing specifically on this sample from Brown et al. So these 6, they're all in the inner halo of the Milky Way. That is, they're within roughly 0.6 of R veer. This is not correct. That should be in units of R veer. And the issue is that that's where the things that were accreted a long time ago were. So it's difficult to disentangle something that was quenched via reionization and something that just fell in a long time ago. So you might think that the best thing to do would be to go out and observe the star formation history of something like ARI 2 or some other field ultrafaint, and that would be the best way to tell whether or not it was quenched via reionization or environment. Again, I don't think that's the case because of the backsplash problem. But I do think that instead, we already have the answer if you just take the whole ensemble of ultrafaints. And so here we're just taking, this is very preliminary results from KD, Rodriguez, Wimberly. If you just take those 6 ultrafaints and say, what are the chances that all 6 were accreted by a given redshift? Right? So you can do the same sort of game, do abundance matching, and keep track of when they were accreted. And what you get is a plot like this. So this is the probability in log space that the 6 randomly selected subhalos were accreted as a function of redshift. And so basically there's 0 chance that they were all accreted by redshift 2. And then you start to get the different lines are indicating uncertainties, probing systematic effects with mass that you select your subhalo, distance you select your subhalo, so on and so forth. But the upshot is having just the 6 ultrafaints from Brown et al. To be as old as they are is very unlikely. I'm being as generous as I can here. I'm saying I'll allow them to be quenched at redshift 1.5, whereas all their star formation history suggests they're older than that. It's a 1 in 100 thing at best. And that's only made worse when you count up to 10. And so I think this is probably what many people already assumed, but you can actually look at it in detail statistically, and we can show that it's definitely unlikely, and we don't need, if you're reading an HST proposal, to do the star formation history of ARI 2. We don't need to. We already know the answer. I'm sure that already got approved, actually. So we know, I think we have a very strong case that the ultrafaints are quenched by reionization, or at least not environment. And so at the end of the day, I think this is the takeaway, is that this is what the picture of satellite quenching looks like at late times. I think we can remove that question mark there, that with some rough uncertainty at the boundaries, you have starvation at high masses, you have stripping at low masses, and then at the very lowest scales, I think there's some question about where exactly this is, but that it's clearly reionization takes over. And so I will end perfectly on time.
What is the frequency scale?
It's just the accretion of subhalos. You can't get that many accreted. If you take the distribution of infall times for low mass subhalos, they're distributed across all of cosmic time, and to randomly pick 6 and get them to all have fallen in early, such that environment could quench them, it just doesn't work. That's just with 6, but we have star formation industries for about 10, 11, done with HST, down to roughly the oldest main sequence turnoff, and it only gets stronger then. Phil.